give it strength. If I take it and anneal it or hold it for a long time at 110 degrees centigrade, after about 300 or 400 days, if I want to do a heat treatment for a year, I can get the maximum strength, the maximum hardness, which is related to strength. 130 is also pretty good, but again, we're talking ridiculous times. If we want to get down to reasonable times, 1 to 10 hours, I might use 165C, and that's why before the 340F you got to convert, because some of these metal just don't speak centigrade like me. Okay. Now, these temperatures are not that hot, and so you have a problem. When you're welding, you're certainly going to overage a lot of these things in the heat effective zone. The Concorde, the SST, that the French and the British flew, was not limited in speed, it was limited by skin temperature. They had heat-treated aluminum alloys, and they had thermocouples to measure, or temperature sensors, to measure the frictional heating in the atmosphere that day. On a really cold day at 60,000 feet or whatever altitude they were going to fly at, on a really cold day, like minus 60 degrees centigrade, they could go across the Atlantic faster. Okay? On a warm day up there, minus 30 centigrade, less cooling, the frictional heat on the skin, I can't remember, I think I knew once, they couldn't exceed something like 200 degrees F on the skin, or they were going to get into this over-tempering, and the life of the aircraft was going to be shortened significantly. You needed a life of the aircraft that's going to go out here to 10,000 hours or something, okay? So when they said, oh, we're going to retire them and stuff, they made a big deal of it because they had this crash of one of them in Paris because it was taking off, and the aircraft ahead of it had dropped a piece of trash on the runway, and the Concorde hit it and caused it to crash, and they said, oh, we're going to scrap the fleet. They were about ready to scrap the fleet anyway, okay? It was getting past its useful life, so this was just an excuse, okay? I actually ended up having to work for the company that dropped the trash on the runway. But anyway, okay. Any questions on that stuff on aluminum? That's sort of a basic metallurgy of aluminum. Easy to weld, the heat treatable alloys. You can put enough alloy content in to the ones that are slightly work hardened in the 5000 series that you can get basically 100% strength joint in a 5000 series weld. So if I'm making some aluminum ship, and the Navy makes lots of hydrofoils nowadays and lightweight ships, and they're using 5000 series non-heat treatable alloys. They don't have strengths of 60 and 70 KSI, they have strengths of 25 and 30 KSI yield strength. Yep.
In terms of these 5000 series for bolts, I know it's used for both. They use
Yep.
3000 or 5000. The question I had was with respect to corrosion, is there limitation in terms of how you're going to do the welding portion like this to try
Yes.
the risk of getting corrosion?
Yes, there is, and let me jump ahead a little bit. There are some significant limitations. Which filler metal you use makes a big difference in the subsequent properties of what you're going to end up with. As I said before, you want to use a filler metal that either keeps you very lean in alloy or very rich, which means you don't want some filler metal that when it mixes with the base metal gives you something here in this easily cracked range. So if I'm using 3000 series alloys, which are way over here, I can weld them with 1100 aluminum, nearly pure aluminum. There's not enough alloy, you'll never get over this way. I can use 4043 filler metal, which is aluminum, very high silicon alloy, and my weld metal will end up over here somewhere. Okay? I don't want to use some alloy that's going to put me in here. So now that I said that, let's see if I'm right. Well, here's the test. See if I pass today. This is a chart of what aluminum alloys can be welded with what filler metals. And so let me just show you the whole chart. And this chart goes on for 2 pages in the welding handbook, okay? So it's 2-page chart. But if I look on here, I should be able to find, here's my 60, 61, where's my 1100 aluminum? So here's my 1100 aluminum, or my 1000 series, or actually you wanted 3000 series. 3004, it says I can use 4043 filler metal. I was right. That's the most common filler metal, folks. I wasn't just sort of taking a wild guess there. That's called an educated guess. So 4043, you can weld something that's very pure with something that's very highly alloyed, and what you get is something over here alloyed with something that's way over here, and the average is right here. Okay. 4043 is just basically an aluminum silicon alloy, very highly alloyed, but you can also use 4145 for 3004. 4145 will give, well, 4043, let me back up, will be the easiest one to weld for the guy making the weld. Whoever it is, man, woman, dog, machine, whatever. Okay. This is the easiest operability. And these little footnotes here, there's a bunch of footnotes at the bottom, and you can look them up, but it will tell you something about that. 4145 is probably optimum strength. 5356 might give you the best anodizing so you can match the color, for example. So there's a whole series of things. Well, actually, it also depends on what you're welding it to, okay? But if I take 3004 to 3004, I can go across here and I'll probably find, it says 5356. I guess I was wrong if it's 3004 to 3004. But if it's 3004 to 1100, it turns out I was right. 4043 is a good one. But it's a complex chart to look at what filler metal. And what I'm going to do on Friday is I'm actually going to take you through some free consulting I did for a shop, I mentioned this a little while ago, that repairs aluminum castings for aircraft engines. And they are one of the only shops in the country that's authorized by the Federal Aviation Administration to do weld repair on these castings. Okay, and they had developed a process. I go back and they think they were using 4043 on this particular casting alloy. I had to look it up on here, and we'll go through this on Friday, of how I use this chart. And they said, well, is this the best alloy? Because someone else, there was a crash, and it was in Canada, and the Canadian let's say ours is the Federal Aviation Administration. In Canada, it's the Canadian Aviation Administration, but it's really, you got to say it in French and English in Canada, right? I can't remember what the initials are. I think it's CAA. Do you remember? Okay. What Canadian are you? What good are you as a Canadian? Anyway, so they were being criticized in a report by the Canadian aviation authorities for the filler metal they are using. So they contacted me and said, Tom, we've been doing this since 1976. Should we relook at what we've been doing for the last 40-some years? And so we'll talk about that on Friday. It's sort of a little case study on how do you pick an aluminum filler metal. And it depends, what are you trying to get? Best strength, overmatching, undermatching. We talked about matching of strength yesterday. You want better corrosion resistance. You want better, in some cases, you want to have a color match when you anodize the structure afterwards. You don't want the weld to look like a weld after you've anodized it blue or green or whatever color. And so there's lots of different filler metals that help match these things. I didn't tell you this, but in steels, we have what we call weathering steels. And you have 8018 electrodes, and they have a designation. If you're buying the steel from this steel company that uses this composition for their high-strength steel, you got to use this electrode, which is different than if you were buying the steel from another one, if you want to match the rust color on the weathering steel. Okay? There are lots of little details out there that, it's not worth spending a lot of time on. Any questions in the next 2 minutes? Okay, well, let me just put up, So I think I mentioned before when we were talking residual stresses, when you heat treat aluminum, you get residual stresses through the thickness. I don't remember if I talked to you about this. There's actually a student I'm working with who's doing some stuff, his bachelor's thesis on something called upquenching of aluminum. But anyway, this is aluminum alloy 750 plate and sheet, manufactured by Alcoa. It's an alloy they developed, and of course they're supplying the world's best. I don't know if they mean best products or best companies that they're selling to. They're trying to pander to their customers anyway. But they have a bunch of different heat treatments here. You can get 70-50 up to 6 inches thick. Okay, that's what I want you to see here. Here's another one, up to 6-inch thick plate. It's all made in Davenport, Iowa, on the world's largest rolling mill, larger than any steel rolling mill, because you have enough separating force on a big aluminum rolling mill that you can roll very thick plates, very wide plates. And what do we do with them? We turn them into aircraft wings. Okay? And the Davenport Works makes most of the aircraft wing material for the big Boeing jets and the big Airbus jets and people like that. I don't know, it may be Airbus buys it from somebody else, but when they heat treat this 6 inches thick to get the strength, they got tremendous residual stresses. And residual stresses, when you start machining this, all the little cavities and everything, they may throw away 80-90% of the weight of the aluminum after they take this solid chunk of aluminum and turn it into a thinner section with all these bosses and stuff. You don't want to have to weld it. They machine the whole thing. And they may machine, they got tons and tons of aluminum. They may throw away 80-90% of the weight as machining chips. But it's got tremendous residual stresses. And if you don't get rid of the residual stresses, you're going to have fatigue problems. You can't heat treat it to relieve the residual stresses for various metallurgical reasons. So what they do, the 5-1 is a 1% strain. They have this huge hydraulic jack that can take a 6-inch plate by about 10 or 12 feet wide and just stretch it 1%. Now remember, this is 70 KSI material, so go home and do that homework. 6 inches by about 12 feet by 70,000 PSI, and you're going to do a 1% strain. And how many million tons is that? Okay, I've been to that room. They weren't stretching something at the time, so I didn't see it being stretched, but it's a big hydraulic machine. Okay, just got big jaws on the ends, and they just grab it just like a big tensile machine and pull it 1 to 3% strain.
And that activates the aging as well.
That can activate, yes, that can activate the aging. I'm not going to get into why these are 7.451, 7.351. I mean, there's yes, you're right, it does.
Done after.
Depending on the alloy, yes, it's usually done before. Well, no, you quench it and you age it, but you may do a double age. You may age it to get strength, and then you stretch it, and then you might age it again to get even more strength, or over-age it to get corrosion resistance. I mean, I'm not enough of an aluminum metallurgist to be able to tell you all that.